for the following manufacturing process. This would be the manufacturing process of the excavator bucket, and shown in the previous CAD drawings, we select an ASTM aluminum 6061 T4 sheet of 1/8, 18 inches times 20 inches. We perform the following cut, the geometry specified as in the previous CAD drawings, and drill the hole specified on the previous CAD drawing. Also, for the part of with the teeth, we need to cold stump the teethed individual part of the excavating bucket to the desired angle and weld all parts so it finishes like the finished product shown here in this slide. Shown here is the manufacturing procedure for one of the side plates of the conveyor excavator. These plates are designed to protect the conveyor from debris and other stuff that might get into the inside of the mechanism. We start by selecting another ASTM 6160, this time T6 aluminum 3/8, 12 inches by 48 inches. We insert the drawing format into the CNC machine using the pen drive or SD card and perform the following cut list. The geometry specified cut as shown in the previous CAD drawing, and the drill holes on the plate as specified on the CAD drawing. This is the manufacturing procedure for the motor side plate. This plate is the one that's going to be on the other side of the conveyor and will be attached to both the conveyor and the motor that is going to give function and movement to the excavating conveyor. We select another 6061 T6 aluminum plate with set dimensions, insert the drawing in STL format into the CNC machine using the pen drive or SD card, and the machine should perform the following geometric specifications as shown in the CAD drawing and drill the holes that are shown also in the CAD drawing. This is the manufacturing procedure for the bucket bar plate. This bar plate is going to be the one that attaches the excavating bucket to the chain in the conveyor. We select an ASTM 6061 T6 aluminum plate, insert the drawing again into the CNC machine, and the machine will perform the following geometric cuts and the following perforations as shown in the previous CAD drawings. This is the manufacturing procedure for the belt plate. As in the previous chain belt plate, we use the same material and follow the same procedure as insert the drawing in the CNC machine using the pen drive SD card and perform the following cut list, that is a geometry specified cut as shown in both CAD drawing and drill the holes that are shown in the CAD drawing too. In this slide we show the manufacturing procedure for the conveyor frame. Notice that it is a compilation of different parts that are going to be welded together, and all the dimensions are shown in the previous slides, with made from an ASTM 6063 T52 aluminum rectangular tubes with set dimensions. We follow the same strategy as the previous design items. The geometry specified cut as shown in the CAD drawings, and the plate and the holes on the plate that are specified on the CAD drawing. After all the items are both created, we weld the tubes as shown in the conveyor frame CAD drawing and as shown in the finished product. This is the manufacturing procedure for the tension system. It is made of aluminum 6063 T52, as same as the previous slide, the previous manufacturing procedure that I explained. We're gonna follow the same strategy. We're gonna divide the system into different parts and design those parts with set specifications, and then weld them together as shown in the final product. For this part, this is the rear shaft. This is the one that's gonna give the movement with the servo motor to the conveyor. We utilize aluminum 6061 T6 651 rod. We utilize a lathe machine to reduce the diameter as shown in the drawing of 75 inches to the specific length of 225 in one side and 0.53 on the other side. We utilize the milling machine to mill the trench on both sides with the depth as shown in the CAD drawing until we get the final product shown here. And this is the manufacturing process for the front shaft that's gonna give that is gonna help the conveyor belt move. We utilize the same procedure as the previous one, with the exception of milling the trench on one of the sides of on the sides of the shaft. We only utilize the lathe machine to reduce the diameter of each end from 0.75 inches to 0.59 inches as shown in the CAD drawings. This is the conveyor body rod. As shown in the previous slides, we have two rods of different length that are going to be attached to both the bars that are going to hold up the conveyor and the body or frame of the rover. They're made out of AK Steel 304 authentic stainless steel rod of 0.5 inch diameter, and the length of both of these rods are shown in the previous CAD drawings. And for the manufacturing procedure, when we get a 50-inch long rod, we're just simply gonna cut it to the specific length that our CAD drawings show us. And this is the manufacturing process for the conveyor to frame plate. This is the main part that's gonna hold the conveyor excavator to the body. It consists of aluminum 6061 T6 with set dimensions. And for the following procedure, it is an aluminum square tube. We're gonna saw it to the dimensions and then punch the holes that are shown in the CAD drawings until we get the finished product, that is this here that it shows.
Good afternoon. Today we'll be going through the manufacturing procedures for every part of the mining rover. Firstly, we'll be talking about the main support. We selected an STM6061 aluminum tube of 1.25 by 20 by 8 0.87 of diameter. To the procedure for this one will be mainly we need to measure the aluminum tube to place the marking on the 38 inches, which is exactly in the which is to perform a cut on the specified geometry of the marking placed on the tube. We'll be doing this with the aluminum saw we have right here, and the material will be, like we said, the aluminum 661, and this will be the finished product of the material. For this slide, we'll be actually going through what will be the square upper support. This will be the third drawing, which will be making the upper support, like we said previously, that helps to prevent the load that is exerted on the upper part of the rover. Like previously, we're using STM 6061 aluminums, which is the 6061 aluminum alloy. It will be a square tube of 1.25 diameter by 0.13, and this will be the diameter of the current tube. We'll measure the aluminum like previously and place the mark in the 28-inch mark. We'll be cutting it with the aluminum saw. And like in the inner support, we'll be performing a cut in the specified geometry of the marking placed on this tube. And perform finally the milling of 0.63 radius on both cut ends of the tube. So both ends that we cut it will be placing this milling in it so we can actually weld it later on with the main support and inner support of the rover. For the fourth CAD drawing, we'll be talking about the cable box supporters. For this one, is a little simpler design. We'll be actually selecting an STM6061 aluminum plate that is around 0.30 inches thick with a 10-inch width and 8-inch length. This CAD drawing will be inserted into a CNS milling machine. Software using the USB drive will be the machine that we have right here, and perform cut on the CAD specific geometry. This machine will actually help us determine the area that we need for the support and actually cut around it, giving us the piece without any human error or any error on our part that we could actually get injured. Then we're going to perform a cut in the CAD specific geometry, which will be the holes that we'll be drilling in the specific place that the CAD drawing already showed us. For the motor saddle, this will be actually one of the main parts that will be manufacturing. This is the one responsible for mainly holding the motor of what will be the wheels of the rover. Like previously, we'll be selecting an STM aluminum 6061 plate that is around 1 inch thick and 10 inches width and 8 inches length. We'll be measuring the plate and mark the length of the in the CAD drawing. Later, we'll be inserting the drawing into the CNS milling machine software using the USB drive. Perform the drill holes on place as shown in the CAD drawings. Mainly we'll be inserting it into this specific machine, and we'll be using later on the drill bit after the cut has been done to drill the holes that we'll be using to put the screws on. Here we have what we call the wheel motor compartment. This is responsible for holding the wheel motor. This actually have to go throughout the design since the motor we actually need to move the rover tends to be a little bit denser and heavier and in a square root. So we actually decided to do this type of square to hold the rover motor without problems and even helps us to actually get more central place of gravity in the rover in the final design that we took. For the manufacturing process of the motor housing, this will be actually one of the most challenging manufacturing procedures. Mainly, we'll be selecting a solid cube of aluminum 6061. Will be a block around 10 by 10. We'll be inserting the CAD drawing in a CNX milling machine software using the USB drive. This actually will help perform on the milling and the block to the specific geometries on the CAD drawing. Later on, we'll actually perform a hollow in the piece by inserting the CAD drawing onto the next milling CNC. This will perform the milling on the piece to hollow the specific geometry of the CAD drawings, will be the geometry already placed in the part of the project. Finally, we'll perform a cut in the CAD specific geometry, and in the end, we'll perform the drill holes on the square beam shown in the drawings. This will actually give us the area where the motor will be actually hooked on inside the motor. Here we have the next part of the will be part of the rover wheels. These actually are the rover wheels itself, which will be made by an aluminum XTM 661 aluminum block of 15 by 15. We'll be inserting the CAD drawing into the CNS lathe machine software using the USB drive like previously. Well, after the aluminum block has the circumference specific to the drawing geometry placed on the CNX milling, we'll be inserting the CAD drawing into the CS milling machine software using the USB drive to perform the cut on the CAD specific geometry, later on with the drilling bit. And finally, we'll drill a hole in the finished wheel to create the center of the motor. Mainly, we're using first the CNC lathe in the block to actually have create the round part of the wheel and have the correct circumference to later use the CNC milling lathe to drill the holes and the parts of the wheel that will make the inner rim. And finally, we have the cable box. This is different from other the previous builds because we'll be selecting a dendritic filament, which is a type of polymer. This CAD drawing will be inserted into a 3D printer software using the USB drive, and we'll be performing a cut on the already printed box on the CAD specific geometry. And finally, we'll drill the holes on the place specified by the CAD drawing, like was in the picture right here. We have the 3D printer we'll be using and the drill bit that will be drilling the holes into the cable box. And finally, we'll be going through the assembly of the main body of the rover. Firstly, we'll be using the assembling component of the main support, internal support, the square upper, support cable box supporters, motor saddle, motor housing, rover wheels, and cable box will be shown here. And we'll be fastening this and using together a ceiling hex head screw that is around a quarter and 13 and a machine thread that will be used to hold the box in the back panel of the rover, and the hex nut to tighten the screw. And to unite the main support, the internal end square will be using a MIG welding method at a preheat temperature of 150 to 200 Celsius applying the aluminum. This actually helps us not to damage the aluminum and even strengthens the bond, the connection between both pieces. And the assembly diagram will present here the raw materials that will be the main part of the rover, and the finished product that is the main body of the rover already built.
Here, Professor, I'm going to be explaining the new electronic devices that have been added in order to properly explain in the following slides in the electrical architecture that has been designed and tested and taken into consideration with regards to the rover's controller operations. In order to understand some of the finer details of the smaller components of the electrical architecture, I have devised these two tables that will explain some particular components, such as the coupling conductor, the recoupling conductor, transistors, slightly larger components such as the decoder, the servo motor driver, the power regulator, and the receiver. They have a brief description, as you can see right here, but to go a bit more in depth with them, essentially they are necessary to alternate things such as a noise cancellation of the signal feedback error, in other words, the typical noise factor of anything system control related, as well as to amplify signal transitions between component to component. For which is why we mainly have things such as the coupling conductor and the recoupling, the decoupling conductor and the coupling conductor. Transistors also act as amplifiers, but they're mainly used for more critical components, as you will see later on in the diagram itself. As for the slightly larger components, such as the decoder and so on, the decoder, first of all, is essentially the twin of the ASC transmitter that will be found in the main handheld controller of the rover's operation. The decoder essentially takes the information from the ASC transmitter and essentially interprets it so that the controllers inside the rover itself understand what it is that they're being asked to do, the proper command, if you will. The servo motor driver is an essential piece of anything involving servo motors. Essentially, they regulate every electrical signal that flows through the system and allows for a proper usage of the servo motors themselves without excessive RPM disturbances or excessive RPM inputs that the user might try to apply on. The power regulator is a vital device for safety hazards, given that there could be situations where the system itself might overcharge or might give off an excess amount of power that is not necessarily asked upon from the user. If not, it is simply a physical reaction that happens between the electrical components, something outside of the user's control. In order to avoid these things, we have a power regulator that essentially monitors and in certain cases can even purposely reduce the amount of power that is flowing into the system. And finally, the receiver is essentially another component, the other slash component decoder that is coupled with the decoder itself, and it is all part of the transmitting controller unit. Here we have the main electrical architecture diagram that governs the entire control system of the rover as it stands right now. As I have explained before, there are a lot more considerations of more specific electrical components that have to be taken into consideration in order for this to properly work. Signal feedback errors are not the only parameters that I have to think about for when it comes to the design of the rover. The rover is going to lash out, so to speak, with all manner of extreme or possibly insignificant electrical signals that all have to be interpreted by the same controllers that I have at hand. These smaller components, they aid us, of course, in the proper distribution of set signals and electrical power outages. They allow for a smooth transitions. They allow for more a strategic use of electrical connections, and of course they allow for an overall efficiency of the system. And as I've explained before in the flow charts of our previous phases, of how it is that this is going to work from the power source of our 120 AC volt battery, we're going to transition into the decoder itself that is aided by the receiver. the receiver in of itself, and the decoder act simultaneously to produce us with a proper operational command data that then the controllers can use to manifest their own commands, and for them to use that translated information into the subsequent controller PID controllers. These PID controllers have been properly calibrated in order to be more of, let's say, integral PID controllers over proportional PID controllers, given the situation and the nature of what it is that we have to develop. As explained before, the rover PID controller is going to simultaneously provide a signal input into 4 individual PID controllers that then they themselves are going to control the 4 servo motors themselves through the usage of the key element here, which is the servo motor driver. The servo motor driver is aided by a smaller conductor that is going to help regulate the amount of signal that is going into the driver itself, so that situations such as miscommunications or lack of proper data information transfer flows from the controllers into the driver itself. I did discuss this with colleagues, and I have discussed this with even professors that know more than I do about the subject, and they have assured me that the wheel driver, servo motor driver, is a necessary component, that it cannot just be replaced by simply the existence of another controller. That then they later flow into the parallel assembly that we see here of the servo motors. To them they later feedback through their integrated tachometer sensors, and then they feed back into the controllers for them to display and give us real-time adjustments of the speed regulation that is necessary for the proper for these stabilization situations that may arise from the uncertainty of the environment at hand. Here, Professor, I'd like to gloss over in more detail what it is that we expect the user to take into account from when we talk about the safety and the safeguard measurements that have been taken to properly utilize our modem operandi for the beginnings of our modem operandi with with concern to the rover. Essentially, we request that the users carefully read these instructions and for them to follow them to the letter in order for them to properly use the rover itself, as well as to be safe as we proceed with using the device. As we can see, I have displayed a series of bullet points in regards to what it is that it is necessary to comply with in order to properly use and to be safe using the rover as it stands. Things such as to deploy the rover on a flat surface, or possibly not so much of a undulated surface with rocky terrains, uncertain geometries, unforeseen obstacles, and everything of the sort, to acquire the proper regolith recollection. And of course, to place it in an area for where it is that you need the substance to be found, a regolith rich deposit area. Of course, to carefully unload dirt from the bucket itself, seeing as it is a integrated and solidly placed element of our rover that could be modified later on down the line. But as it stands, it's a fixed component that one would need to cup or to grab a possible smaller recollection cup to then extract the regolith from, as well as to always verify that our control panel, our cable box, in other words, to be properly activated, fastened, calibrated, and everything of the sort, which will be explained later down in the instructions. Of course, to never set the rover to extreme velocities, regardless of the motor's capacities as they stand, because they are capable of giving off incredible RPMs that could be hazardous for the user and the rover itself. The equipment could be possibly tumbled. It could be turned over. They could be in great danger and can produce dangerous hazards such as projectiles flying everywhere. Pieces could be dismembered from the main body and can act as projectiles and that would place people in the vicinity in immediate danger. Extreme velocities are advised against in this in the usage of this rover. More so than that, we advise that the user should stay at a minimum of 10 feet away from any given operation that the rover may be undergoing, mainly the excavation portion of the rover itself. To not replace the rover battery with possibly something like a car battery or anything that of a lower capacity. This will offset the electrical outages and the inputs into the system and could produce irreparable harm into the system itself. To alternate, sorry, to never overflow the recollection bin, given that it could spill over, you could lose, precious regolith or the samples that you are interested in. To then later have, let's say, a situation where it's already overflowing, there could be a problem of stabilization that the system can't account for, and so the entire rover could spill over in something of an extreme situation. Of course, to never use the mining rover as a means for construction or landscaping. This rover is simply for the purposes of recollecting samples, earth samples, soft earth samples, for the purposes, of course, of scientific research and analysis. Of course, to always maintain visual contact through the integrated camera that will be provided later down the line with the finalization and the final design of the rover at mid to long distances, seeing as it has the capacity to go forth into a field with said capacities. Here we have some easy to follow instructions in regards to not the immediate operation of the rover, if not the initial installation and usage of the rover itself for when it is placed on the ground of operation, or rather if it is that you want to pre-calibrate it before heading into the field of operation. Firstly and foremost, we deeply encourage the user to follow these instructions in before applying any type of controls into the rover itself. To first use these instructions on the rover itself, to then later activate the remote control and do any further calibrations that the controller itself, its information might request of you. But now for the real instructions of the rover itself, we have for each PID controller, we urge the users to activate the controllers with the up and down button simultaneously pressed in order to open the entry display options that they will cycle as you press the further independently up or down of any given display. There is an array of them, but only the following are the necessary ones in order to properly calibrate each PID controller. Firstly, we'll need to enter the set desired value that will be displayed in red in the main display itself. This could be anything from within 5 meters per second to then later possibly 15 meters per second. As an estimated guess example value, to then later confirm the set value by pressing the set button itself. For more precise signal feedback remote control, which we deeply recommend, you can cycle through the displays after having inserted the set primary button values by cycling through the displays, as I mentioned, until you find the UPS display. For when you are on that, you will press your desired maximum speed values, which will, in any case, for when you apply that, it ensures that you will not go beyond said limit of operation with regards to speed. And finally, the final step would be to set the lowest value so that it won't ever devalue, it won't ever decelerate below the desired value, unless the controller users itself, the user's controls decide to completely stop the operation altogether by letting go of the joystick of the controller that we'll see later down the line. As we have right here, this is the Burnmouth VXU controller that can be used for a multitude of operations in regards to servo motors. It is, as you can see in the display, the example display that we see here is in regards to a drone that can be utilized through this controller. It has a display camera that is hooked to a integrated camera depending on the system that you're using, but the extreme advantage of this particular model is that it can serve as an adaptable controller piece for any type of controllable or programmable vehicle, a small grounds vehicle or possibly aerial vehicle. In the case of ours, it would be for, of course, the mining rover. In regards of how it is that we've applied the controls of the rover, it is as follows. As we can see to our left, we have the joystick with the main rover movement operation, the typical forward, backwards, left, and right, that can be obviously easily programmable once reaching that point of the development. We have to our immediate right, to our far right, we have the joystick that controls the monitor surveillance camera that will be in charge, as I explained before, of monitoring, of course, the operation of the rover, but as well as the conditions of the components themselves, if it is that they are undergoing a lot of excessive use, possibly smoke hazards, or possibly catching on fire, so on and so forth, so that the user has an idea of what to do in such situations that the rover might be out of view of the user. And on the upper flip-up switches, we have the conveyors functionalities, the more specific functionalities of the excavation process, which is the up and down functions of to have the conveyor lower itself diagonally in order to make contact with the regular ground, as well as the flip switch for the conveyor function of simply activating the servo motor that is in control of the excavation process. And finally, as you may have noticed by now, right in the middle, and or rather above to the right of the bumper controls, we have a small, rather hidden, it can be, it's a little bit hard to see, but it is the simple push button that simply deactivates the entire system, or rather it deactivates the controller itself. And to be more precise, as for it, when it is being deactivated, it will halt the entire operation of the rover at a remote distance, of course. And the only other detail worth sharing is that the button itself has a safety feature of only being able to be turned off under the pressing of it over 5 seconds, as well as for turning it on for safety reasons.